Okay, so today we want to kind of change gears just a little bit. We've talked about covalent bonding quite a bit and how to draw it on paper and structure it with Lewis structures. Today we want to talk about the other two types of bonding, ionic bonding and then a little bit less metallic bonding. So remember that for ionic bonding, electrons are transferred. Okay, so we have positive or negative charges. Okay, so we have plus or minus charges there. So we have either cations, so that's something with a positive charge, or anions, something with a negative charge. And we know how to find the charge that an atom would have. If it does form an ion, we go to the periodic table. We remember the charge pattern. We remember +1, +2, +3, skip, -3, -2, -1. Okay, so we can find that. So once we identify a bond as being ionic, really, when we diagram it, all we have to show is whether or not it has a positive or negative charge, and then we show the correct number of atoms involved in a bond. So let's look at what I mean there. Let's start off by looking at the combination of sodium and chlorine. So to start off, sodium would be in group 1A. So sodium would have one valence electron. Chlorine would have 7 valence electrons. It's in group 7A. Okay? So when the electron is transferred, this electron goes right here. So we're left with sodium with a +1 charge. And we have chlorine with a -1 charge. Okay? So we go back and check ourselves. Those are the preferred charges. Okay, sodium prefers a +1 charge, chlorine prefers a -1 charge, so we're good there. So here's a note. The charges always have to equal 0, okay? So the positive and negative charges always have to equal 0, and overall it must be neutral. So a +1 charge and -1 charge, and this is the way we show sodium chloride here, okay? We just show plus charge, negative charge, they are electrostatically bonded here. Okay, so the negative charge attracts the positive charge, and that's what holds them together. Excuse me. You don't show a bond here. There are no electrons being shared. That's all we have to do. So we see that the positive cancels the negative, so we have one of each. So we have NaCl as our formula there for sodium and chlorine bonding. So let's look at calcium and iodine now. So calcium is in group 2A. So calcium starts off with 2 valence electrons. Iodine is in 7A. Okay. So it needs one more electron. So we know calcium likes to give up its electrons and have a +2 charge. But this iodine can only take one electron, because if it takes one electron it has 8, so it's good now. So we actually need 2 iodines. And then the other electron will go to another iodine. And there, I shouldn't have crossed arrows there, but I did. So now after this transfer, we have a calcium with a +2 charge. And we have 2 iodines, each with 8 valence electrons, each with a -1 charge there. Okay? So hopefully you see why we needed 2 iodines, because calcium had to lose 2 electrons, and each iodine can only accept 1 electron. So now we see, does the overall charge equal 0? Yes. 2 minus 1 is 0, and we see the atoms have the correct charges. If you look at the table, calcium prefers a +2 charge, iodine prefers a -1 charge, so we did that correctly. So our formula would be CaI2. Because I need 2 iodines for every calcium. Okay? So this is what we call our formula, or our formula unit. Okay? So if I have a bunch of sodium chloride, a bunch of table salt, I have many atoms, but they all are derived from some combination of this ratio. For every chlorine, there is 1 sodium. So if I had calcium iodide, there's a bunch of calciums and a bunch of iodines, but there are twice as many iodide ions as there are calcium ions. So this is the formula unit. This is the smallest ratio that we can have for these atoms when they combine to form an ionic compound. So we don't always have to show this process. I'm just showing it to you here so you have a general idea of what's actually going on. So if you get to a point where you don't need to do this, that's perfectly fine. But I'm going to do it now. This is what I need to see though. This is what we want to see for the ionic compounds. That's the final answer we're looking for. So let's go ahead and look at another one. Let's look at potassium and oxygen. Okay, so I have potassium with 1 valence electron, oxygen with 6. Okay. So potassium is going to give oxygen its electron, but oxygen still needs 1 more electron, so it has 8. So I need 2 potassiums. Okay. So now I have 2 potassiums, each with a +1 charge. Then I have an oxygen with 8 electrons with a -2 charge. Do the charges cancel? Yes, I have -2 + 1 + 1, so that's equal to 0. So my formula here would be K2O. So this is how I show this ionic bond. I just have the ions and the charges are holding them together. So I do not show the bonds there. Okay? So for every oxygen in an ionic compound of potassium and oxygen, you have 2 potassiums here. That's how the electron transfer works out there. So let's look at another one of these. Let's look at aluminum and oxygen. Okay? So if I have aluminum and oxygen, oxygen starts off with 6. Okay. Aluminum starts off with 3. Okay, so aluminum is going to transfer its electrons to oxygen because aluminum prefers the positive charge. Oxygen prefers the negative charge. We learned the charge pattern. So I can say these 2 electrons go to oxygen, but it can only accept 8, so that's all it can handle. So I need another oxygen. Okay. So this electron is transferred to this oxygen, but oxygen still needs 1 more electron, so I have to have another aluminum. Okay, so I can put 3 electrons around aluminum. So one of these electrons is transferred to this oxygen. Now this oxygen is good, but I still have to get rid of these 2 electrons on aluminum. So I need another oxygen. So these 2 electrons go down to oxygen. Okay, so now finally, every oxygen has 8 electrons, and every aluminum lost all its valence electrons. So these oxygens all have a -2 charge. These aluminums each have a +3 charge. So I can show this in the simplified form. +3, +3. I'm going to show my oxygens with 8 valence electrons each. They each have a -2 charge. So I'll go back and double check a few things. Do the atoms have the correct charges? Yes. Aluminum prefers a +3 charge, so that's good. Oxygen prefers a -2 charge, so that's good. And the overall net charge is 0. +3, +3, -2, -2, -2 is 0, so I'm good there. So the formula unit, or formula for aluminum and oxygen, when they bond together ionically, is Al2O3. Okay? So this is the process we'll use when we have ionic bonds. So if we do not have electron sharing, so we have a metal and a non-metal, we'll use this process to kind of show the bond. Okay, so this is what I want to see here. If I ask you to diagram the bond or show me the bonding, what's going on, we don't show any kind of lines connecting these because that would imply that electrons are being shared. So we can have a situation where we have ionic bonding and covalent bonding present in the same molecule. So let's look at the example of sodium and nitrate. So I won't show the electron arrows. We really don't need to see this on paper. I just showed you this to make sure you understand what's going on. You don't never need to draw this. That's not necessary. So we already know that sodium is going to form a +1 charge. Nitrate is going to form a -1 charge. So I could do this in brackets. Sodium +1, nitrate -1. That's not incorrect necessarily, it's just not fully correct. Okay, that doesn't show me what's going on between the nitrogens and the oxygens. I need to know what's going on there. So if this is the correct answer, what I should show, show sodium, it lost its valence electron +1, then I should show what's going on with nitrogen and the oxygens. So I'm just drawing the nitrate that we looked at in the previous video. Okay? And if you want to draw it in a different form, that's perfectly okay. So now I show that the polyatomic ion nitrate is covalently bonded together, but the sodium and nitrate are held together via ionic bonds. Okay? So when you have polyatomic ions that participate in ionic bonds, and again we know it's ionic because nitrate has a -1 charge, sodium has a +1 charge, it's a metal and a nonmetal. When you have a polyatomic ion present in an ionic bond, you will have covalent and ionic bonding. Okay, so you can have both of those together there. So then the formula would be NaNO3 here is how I would simplify that. Okay. So hopefully you see that drawing ionic bonds are very simple. These were a little bit trickier because we just said potassium and oxygen, or aluminum and oxygen. We didn't give you the formula to start off. So if I'd given you the formula to start off, something like Mgi2, that would make it very, very simple. So that's the case we'll see most often, where you have the formula, then you just show me magnesium with a +2 charge, and 2 iodines with a -1 charge. Okay? So that should be a lot easier for you than covalent bonding. So then we'll look at the last example, metallic bonding. So we won't spend a lot of time discussing metallic bonding, but it is worth looking at. So metallic bonding, we remember the phrase we used to describe it was the sea of electron model. Okay, so the sea of electron model is something that looks like this. So if you have a metal or a bunch of metal atoms that are bonded together, I'll just show the nuclei of the metal atoms as plus signs. And you have electrons kind of freely floating in a sea of electrons, or an ocean of electrons. So in ionic bonding, the electrons were in a fixed place. Okay, they were on the anion. In covalent bonding, the electrons were on a fixed place. They were being shared between two atoms. But in metallic bonding, the electrons are what we call delocalized. So they can move kind of freely. They aren't stuck in place. So the electrons kind of go wherever they want to. So there's no great way to show this because there's no definitive place they are. They can pretty much move freely. So for metallic bonding, that's all we'll worry about for now. Just be aware of the sea of electrons model. But we won't ever diagram that because there's no good way to diagram it. We're going to focus on diagramming the covalent and ionic bonds. Okay? So in the next video, we'll come back and we'll discuss the geometry or the shape of covalent bonds. We won't discuss the shape of ionic bonds. So the ionic compounds typically form what we call a crystal lattice. So a crystal lattice is just the regular repeating crystalline structure that most ionic compounds fall into. So it's just a nice regular repeating pattern, so we don't need to discuss that. But we will discuss the shape or geometry of covalent bonds and covalent molecules moving forward.